Hello everyone, I'm Yufan from Chen University. Today I'm excited to present our work on identifying and exploiting semantic gaps between zip parsers. Let's start with a simple question. If I give you a zip file, what do you expect? You'll probably assume that no matter what tool you use, let it be in WinRAR, SamZip, or any other software, you'll see the same contents. But what if that's not true? What if WinRAR sees one set of file, but SamZip sees another, or from the exact same zip file? This is not a hypothetical situation, it's a reality we discovered. The same zip file can produce different outputs depending on the parser, a phenomenon we call a semantic gap. This might seem like only a quirky bug, but it has serious security implications. Imagine an attacker crafting a special zip file. When it passes through an antivirus scanner, the scanner sees only a harmless file and lets it through. But when the victim opens that same file on their machine, their uncovered extracts a malicious payload. Then the user's system will be infected. So why does this happen? The core issue lies in zip parsing ambiguities. The zip file format, originally created in 1989, has a complex structure with redundant metadata. The official specification is often vague, leaving many details to the implementer's interpretation. Because zip is used so widely, we have a large number of different parsers and applications, each with its own quirks. While individual vulnerabilities have been reported before, there has been no systematic study of these inconsistencies until now. To systematically uncover these semantic gaps, we built zipdiff, a differential parser. In each iteration, zipdiff takes the seed zip file from the corpus, applies a series of zip level and byte level mutations, and then feeds the resulting file to all tested zip parsers. It calculates hash values for the outputs and compares them to detect inconsistencies and guide future mutations. The mutation rules are selected based on the UCB algorithm to balance exploitation and exploitation. Only the interesting samples will be returned in the corpus, which are determined based on the set of inconsistent parser pairs. Please refer to our paper for more implementation details. We used the zipdiff to evaluate 50 common zip parsers written in 19 different programming languages. This includes well-known libraries and applications such as WinRAR, SamZip, LabZip, and so on. The results were staggering. Out of 1,225 pairs of parsers, we found that only 4 were consistent with each other. This means that for almost any two zip parsers you choose, we can craft a zip file that they will interpret differently. Here, inconsistency is not the exception, it's the norm. Note that in our evaluation, two parsers are considered inconsistent only if they both successfully extracted the same file but produce different contents. If one of the parsers detects an abnormality and reports an error, we still consider the pair consistent. Through our analysis, we categorize the 14 distinct types of parsing ambiguities. These fall into 3 main groups. First, confusion over redundant metadata, such as file names and file sizes recorded in multiple locations. Second, differences in how file passes are processed, such as how they are normalized. Third, disagreements on the fundamental structure of the zip file itself, such as the location of the central directory. You can find a detailed analysis for each of the 14 ambiguities in our paper, along with corresponding construction code in our artifact. Now let's talk about how these ambiguities can be exploited. Our first scenario is bypassing secure email gateways. As we saw earlier, deep parsing ambiguities can be leveraged to bypass antivirus scanning. This is less of an issue for host-side antivirus, which typically includes unaccessed scanning as a second layer defense. These systems can scan contents when the zip file is extracted, even if the virus is not found when it was inside the archive. However, email gateways operate on the server side and have no access to the extracted contents on the host machine. For example, Gmail scans attachments and displays a scanned by Gmail message when no virus is detected, and the user may trust the message and then trust the contents inside the archive. We tested 10 popular email providers with antivirus functionality and successfully crafted zip files to bypass all of them. Before we move on to additional exploitations, we need to ask a basic question. What is a zip file? Is it just a file with a .zip extension? Let's see the Word document format as an example. If you try to extract a docs file as a zip archive, you'll see that it's actually a zip archive consisting of a bunch of XML files. Beyond the Office documents, many file formats we use every day are also zip archives under the hood. These include Office documents, Android applications, jar files, VS Code extension packages, and so on. This means that any application that processes these files is, in effect, a zip parser, and likely vulnerable to the same ambiguities. This brings us to our second exploitation, Office document content spoofing. Just like zip archivers, different Office applications may extract or display different content from the same document. A dishonest student, for example, could create a Word document that shows benign content to a plagiarism checker, resulting in a no plagiarism verdict. However, when the same document is opened by the supervisor in Microsoft Word, it displays a different plagiarized content. This technique could be used to evade academic integrity checks. We also discovered a method to forge digital signatures in LibreOffice. We crafted a document containing two different versions of its content. When LibreOffice's signature verifier inspects the file, it checks the original signed content and reports the signature as valid. But when the document is rendered for the user, it displays the manipulated content. This issue also affects the Java ecosystem. Spring Boot supports a nested Java format. It uses Java's built-in signature verifier, but a custom zip content reader. This allowed us to craft a nested Java file that bypasses this signature verification while containing manipulated content. Finally, we discovered an attack scenario targeting the VS Code extension marketplace. A VS Code extension's identity is defined by its publisher namespace and the extension name, such as developer.foo. The marketplace server ensures that a publisher can only upload extensions under their own namespace, preventing attackers from overwriting legitimate extensions. We used a zip ambiguity to craft a malicious VS Code extension package. When uploaded, the marketplace server saw the attacker's authorized ID, attacker.bar, and accepted the upload. But when a user downloaded and installed the extension, Their VS Code client interpreted the extension as having the ID developer tofu. This allowed our malicious extension to overwrite the trusted one. We responsibly disclosed our findings to the affected vendors. We received bug bounty rewards from Google, Coremail, and Zoho for the email gateway bypasses. Our work also led to multiple CVEs assigned to vulnerabilities in Go, Spring Boot, and LibraryOffice. We received acknowledgments from many other vendors as well. For more details and our proposed mitigation strategies, please refer to our paper. In conclusion, our work makes several key contributions. First, we introduced DeepDiff, a differential fuzzer that systematically uncovered semantic gaps between zip parsers. Then we demonstrated that the zip ecosystem is fundamentally fragmented. Almost no two parsers behave identically. Finally, we identified 14 ambiguity types and showcased 5 real-world exploitation scenarios. The key takeaway is this: inconsistencies can be dangerous. We've seen the impact of semantic gaps in zip parsing, and similar issues also exist in other file formats and protocols. It's time to stop being liberal in what we accept and instead enforce strict format validation. Thank you for listening.